students, now let us see another experiment in physics in the section mechanics. What we are going to do here, we are going to arrange a pendulum, simple pendulum, and using the pendulum we are going to find the gravitational acceleration. We usually mark it as g, gravitational acceleration g, simple g, and the value of that we always take it as 9.8 or 10 meter per second squared. That we already know the value and we use that in calculations, but how to derive that value experimentally is what we are going to see now, right. So, look at this, when I say pendulum, a string and a small ball here, right. What you do, you give a small displacement horizontally, then it will start oscillating. How does it oscillate? Let me show it to you. Right, it oscillates like this by a small angle. Don't oscillate it by like 30-40 degrees, must be like 5, 6, 7 degrees in that range. A small oscillation, small displacement has to be given. Why? The time for one full oscillation means, see, it starts from here, it goes up to here and then return and again it goes up. So, starting from 1, 2, 3, coming back here 4, 1, 2, 3, 4 is what you call one full oscillation. From the middle it goes to the right side, comes back to the left side, again it goes to the middle, that is one full oscillation we say. And the time for that oscillation t is given by 2 pi square root of L over G. 2 pi square root of L over G. L is the length of pendulum, G is the gravitational acceleration that we want to find. So, it is very simple, you can see, you measure the length and let it oscillate and find the time for oscillation. T is known, L is known, you can find G. But in physics we usually go for the graphical method. So, if you are going to use a graphical method, what do we do? Square this, T squared, getting squared it will be 4 pi squared, the G comes out and L also comes out, Y M X. We are going to change the length of this pendulum to multiple different values, one by one you change it, maybe like take 50 centimeter, 100 centimeter, 150 centimeter, likewise take different lengths and measure the time and draw the graph T squared versus L. T squared versus L, the gradient of that graph has to give you 4 pi squared over G. Then G will be 4 pi squared over gradient. This is what we are going to do, right? Simple. Few things that you have to note here. One, when you measure L, the length has to be measured from the center of this ball, because pendulum, not only the string, even maybe if you know the length of the string, then you have to add the radius of this ball, so that will be the total length, that is what we mark as L. Basically, length has to be measured from the center of gravity of the ball that we use here. Since we usually use a uniform sphere, you can take the center as the center of gravity, right. So, with the length of string, radius of that ball has to be added to find the total length of pendulum, point number 1. Point number 2, okay, how are we going to fix this on the top? If you take a stand and if you fix it with the clamp of the stand, let us say this is your stand, then you have a clamp here, right. Here if I hang this, what will happen? Let me show you the view from this side. If I look it from this side, how it will look like. This clamp will have a shape, let us say it has a shape like cross section is circular and the string will come like this, right. Now, let us consider different positions when it swings. When it swings, okay, this is one position, this is another position, right. I will draw even more enlarged here. What will happen? Enlarged. Once you have it like this, another position you have it like this. So, what is the problem with this? Length of pendulum changes according to the position. Can you see, when it is at this position, you are going to measure the length from here. Why? From there it oscillates. When the pendulum is at this position, the length starts from here. When the pendulum is at this position, the length starts from here. So, it is not appropriate to rotate that, to rotate that or to coil that string like this. Then this error will happen. That means, according to the position of oscillation, the length that oscillates will differ, which should not be the case. So, how do we avoid that? Right? We take a cork, right? If I show the cross section of the cork, it will have a hole in the middle or a cut like this. So, what you can do, through this cut you can send the string in. If you look from the other side, now look at this, this is how the cork is going to be. So, the string comes through the middle, it comes out like this. So, when it oscillates, from the same point it oscillates, it does not go around anything. Understand? So, that is how we avoid this problem. That is why we use that cork. So, in the exam, if they ask you why do we send this thread or the string through a cork, because we want to make sure whatever the position of the oscillation it is, the length has to be same. Right? To maintain constant length of pendulum, we use this cork. Understand? So, regarding length, there are two complications. Complication number one is this, right? If you just rotate the top of it, top part of the string, if you rotate on something, then around that particular clamp or something, when it oscillates, the length can differ position to position. To avoid that, we had used the cork. Second complication, length has to be measured until or up to the center of the ball, pendulum ball that you are using. Right, that is second complication. Done. Also, when we measure the time, we do not measure it for one oscillation, because the fractional error will be high. Imagine if the error in your stopwatch is 0.1 seconds, and if one oscillation takes 2 seconds, let us say 2 seconds, then the fractional error is going to be 0.1 divided by 2, right, which is very high, which is very high, which is like we can say, if I multiply this by 50, it is going to be 100, it is going to be 5%. 5% error is too big. What we do, we do not measure for one oscillation, we measure it for a number of oscillations, say 20, 25 oscillations. Let us say you measure it for 25 oscillations or 20 oscillations, then this 2 will become 40, 0.1. Then the percentage error is going to be very small, fractional error will be very small, right. 0.1 by 40 means it will be 0.25%. 0.25%. Understand? So, to reduce the fractional error, we do not measure the time for one oscillation, we measure the time for a certain number of oscillations, which is like 20, 25. Another point, the pendulum ball that you use must be made of a highly dense material like a metal. The reason is, if it is heavy only, the impact of air drag, air resistance will be less. Imagine if you are using a ball like wooden ball, which does not have much of weight, then the air resistance will be significant, air drag. Then what will happen? This will come to the like it will not continue oscillating, slowly it will become to the rest position soon. That means the amplitude will start reducing and it will come to the rest position too soon. The damping factor we say, it damps quickly because of the air resistance, right. So, better if we use a metallic ball which is heavy, so that the air resistance can be neglected. So, those are the like factors you have to consider when it comes to the simple pendulum. Now, let us see how we are going to do the experiment. Materials and apparatus required: a simple pendulum, a meter ruler to measure the length, stopwatch, a locating pin and a cork cut vertically in the middle, that is okay. A locating pin, what is this locating pin? When it oscillates like this, perpendicular to this, we will keep a pin here, somewhere around this point we will keep a pin. What is the purpose of that pin? To measure, to find the number of oscillations precisely, because when the thread passes this point rightwards, you start the stopwatch. Next time when the thread passes this point rightwards, first oscillation finished. So, every time the thread passes this point rightwards, you can count the number of oscillations, right. If you keep the pin somewhere here, that is also a method, some books suggest that, but still that might be sometimes bit difficult to find out the correct timing when it passes, because it is the big ball that passes through this, right. So, sometimes you might have confusions where at which point, at like when it passes, this side of the ball passes or this side of the ball passes, it can be a bit of a confusion. Whereas, if we keep the pin perpendicular to the thread here, right, then the error in counting the number of oscillations will be minimized. Clear? That is why we have this locating pin, right. Theory I have already explained, T equals 2 pi square root of L over G, 2 pi square root of L over G, T squared 4 pi squared over G into L, Y equals mx. So, from the graph you are going to get gradient equals 4 pi squared over G. So, G will be 4 pi squared over gradient. Clear? If L is the oscillating length and T is the period of oscillation, T is 2 pi square root of L over G, yes, gradient of the graph T squared against L is going to be 4 pi square over G. So, G will be equal to 4 pi square over gradient. Pass the pendulum string through the cork and suspend the pendulum from a stand. Measure the oscillating length L of the pendulum from the point of suspension down to the center of the pendulum bob. Bob means that pendulum ball that we are using, we call it pendulum bob. Note down the value of L and fix locating pin vertically below and close to the lowest point of the path of pendulum bob. So, here they say lowest point of the pendulum bob, but ideally rather than keeping it there, if you keep it perpendicular to the thread, it will be even more precise. Pull the bob aside till it is inclined by a small angle, oscillation must be for small angle, 5 degree or 6 degree. Release the pendulum to make it oscillate in a vertical plane, and using the stopwatch, measure the time for 25 oscillations. So, 25 is not a hard and fast rule, like 20-25 oscillations you have to take to bring down the fractional error in measuring time. Record the time and repeat the experiment by increasing the value of L by 10 centimeter after starting from about L is 40 centimeter. Now, see, if we have a small stand only, then you can start at 40 centimeter, 30 centimeter, 20 centimeter, 10 centimeter, likewise you can take values. But when change in L is small, understand T is proportionate to root L. So, what difference you are going to see in T is going to be much less. So, it's ideal if we can change the L by like 25 centimeter by 25 centimeter. Or 50 centimeter by 50 centimeter. Bigger the change in L, you will see bigger impact on T. You will be able to measure a significant difference in T. The only problem is if you want to change it by 50 centimeter by 50 centimeter, imagine if you want to get 50, 100, 150, 200, 250, you have to raise it to 2.5 meters. So, raising or setting up a pendulum at 2.5 meters height can be difficult for you in the science labs. But if you have some method of setting it up like that, at least you can keep a stand on top of a table and then keep the pendulum at 2.5 meters and little by little you reduce the length. If you can do that, it's better rather than increasing 10 centimeter by 10 centimeter. If you don't have all those facilities, the normal stand you have would facilitate only for this much, 40 centimeter. Obtain about 5 recordings and enter the values, right. So, this is what the experiment theory and the method is. Now, let us do the experiment, derive the values, we will measure the values, draw the graph and see whether we get G close to 9.8 or 10 as we usually calculate. The apparatus required for this experiment include, you can see this is the pendulum ball with a thread connected to that, right. This is how the pendulum will be set up. Right. We have a longer thread so that we can adjust the length. We are going to take multiple lengths, so we can take different lengths. This is the locating pin or indicator pin, we say. We can keep it like this, right. That will help us to count the number of oscillations. I will show you when we fix it, I will show you how to use this. And we have a cork with a vertical slit in that, a vertical hole. I will tell you why it is useful. Why it is useful. See, if you connect this pendulum on a rod like this, look at this. If this is a rod and if you connect like this, see what happens when the pendulum oscillates like this. When the pendulum oscillates like this. When the pendulum goes to this side, the thread goes around my finger. Can you see? It goes like this. Then the length of thread that oscillates is less because part of the thread goes into rotating the rod or finger. Similarly, when it goes to the other side, the length of thread that oscillates is longer. Can you see? Because it doesn't have to go around my finger, so it goes like this. On this side, it has to go around my finger, so the part of thread that oscillates is going to be less. Therefore, you should not connect the pendulum like this. Then when the pendulum oscillates, the length of pendulum that oscillates changes with the angle. To avoid that, we use this cork with a vertical slit in that, slit or hole. See, I will show you how it works. We fix the pendulum look at this. This is how we are going to fix the pendulum, right. This is how we are going to fix it. You can see here. This is how we fix it. So, what will happen when you oscillate, whichever the side it oscillates, like if you hold it tight, if you tighten this slit, whichever the side it oscillates, the length doesn't change. Can you see that? It doesn't have to go around a rod or anything. Therefore, the length of oscillation always remains constant. Whichever the side it oscillates, the length of pendulum that oscillates, that remains constant. Right. To ensure that, we use a cork with a vertical slit like this. It can be a slit or a hole. Clear? Right. So, that is another part. Then we have this stopwatch, because we are going to measure the time for the oscillation. Period of oscillation is what we measure. So, you need a stopwatch. And this is the meter ruler. Why meter ruler? Because we are going to take different lengths of pendulum and measure the respective period of oscillation. So, to measure the length of pendulum, we need the meter ruler. And this is the stand. You can see I am using an elongated stand, right, because we may be able to use more than 1 meter length, right. We will be using almost up to 2 meters length. When I do the experiment, I will show you. So, I have a elongated stand here. We will be using this stand to fix the pendulum. This is all the apparatus required to do this experiment. Now, let us see how to fix the pendulum and how to measure the time for oscillation. Students, you can see I have arranged the pendulum, the simple pendulum. You can see the thread starts from here, right. from the cork, it starts from here and goes all the way up to here. You can see it goes up to the pendulum, right? The full length of this pendulum now is 175 centimeters. I have fixed it at 175 centimeters. Few things you have to note here. 175 centimeters have to be measured, not the length of the thread. It has to be not the length of the string. It has to be from the point where it starts, from here, you have to measure until the center of gravity of the pendulum ball that you are using there. Right. So, not the length of the thread. You can see here, this is the center of gravity. So, your thread finishes here, but the length has to be measured up to this point. That is point number 1. And the other point, make sure it is vertical. And can you notice there, can you observe there, I have fixed the locating pin or indicator pin perpendicular to the string, right? See, this is the perpendicular, this is the locating pin. Ideally, where we should keep the locating pin is where the thread, the string, where it ends. It must be with the string. Then only you can precisely measure when the string crosses it. Don't keep the indicating pin under the ball, because if you keep it under the ball, sometimes when the ball is passing, you may not be able to precisely measure the point when it passes. So, better idea, keep it across or like perpendicular to the string, right? So, as I mentioned earlier, T equals 2 pi square root of L over G. So, T squared and L are proportionate. I am going to set this pendulum at different lengths, 175 centimeter, 150 centimeter, 125, 175. Different 5 lengths I am going to take, and for each of those lengths I am going to measure T. See, in the string I have marked. Now, this is the 150 centimeters mark. I have marked it here. Then I have marked here, this is the 125 centimeters mark. You can see here, I made a small mark here. And this is the 100 centimeter mark. And this is the 75 centimeters mark, right? So, I have marked it so that easily I can adjust the length of it. Also, when you are measuring the time for oscillation, period of oscillation, make sure the oscillation is not with a wide angle. You give a small displacement, small angular displacement, and let it oscillate within a small angle, because this 2 pi square root of L over G, the equation for period of oscillation is proven for small oscillations, right, not for wide angles, right. So, all what I am going to do, now I am going to give a small angular displacement to this string, to this pendulum, let it oscillate. For 20 oscillations, I have to get the time. Why do we take 20 oscillations time? Because there will be some error when we get the time. So, if you take one oscillation, the oscillation time is very less. When the oscillation time is less, when the measurement is less, the percentage error will be high. To reduce the percentage error or fractional error, what we do? We increase the measurement. That means, rather than getting the 1 T measurement, we get 20 oscillations time. Later, I will divide that by 20 and I will get 1 oscillations time, so that the percentage error can be minimized. Clear? So, this is what we are going to do. This is the experiment we are going to do. Let us start. This is the stopwatch. Let me set the stopwatch at 0. Yes. Let us give a small displacement and measure the time for 20 oscillations. You can see it oscillates. So, how I am going to measure it? How I am going to measure it? When this thread or the string passes the indicator pin towards one side, I will start measuring it. Next time when it passes on the same side, it is 1 oscillation, same direction. Next time it passes on the same direction, it's a second oscillation. That's how we are going to measure it. So now you can see when it passes towards the right side, I'm going to start the stopwatch. One oscillation, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 20 oscillations, I stop the stopwatch. The reading I have got is 53.72. 53.72. You can see it's 53 and 72. 53 seconds and 72. So which I can say approximately 54 seconds, I can say 54 seconds. So when the length of pendulum is 1.75 meters, 1.75 meters, what we get as the time for 20 oscillations is 54 centimeters, right? What we have to do next, now we have done for 175 centimeters, I'm going to change the length to 150 centimeters and measure the time for 20 oscillations again. So how I am going to change it to 150 centimeters, you can see. See, this is where I have made the mark 150. So I am going to raise it up to here. So when I raise it up to here, the pendulum ball also will go up by 25 centimeters. Then I have to raise the indicator pin or locating pin up by 25 centimeters. If not, I can lower the stand, I can bring it down by 25 centimeters. Right, here I have kept the, see, I can lower it by 25 centimeters. Here I have kept the locating pin fixed, right, to show you the observations clearly. Therefore, what I am going to do, after fixing it to the cork, I'll bring down the stand by 25 centimeters up to here. Okay, so let's see. First, let me fix it at 150. Right, now I fixed it at 150 centimeter. I fixed the length at 150 centimeter. Now you can see the ball has come up. It is not near the indicator pin. So what should I do? I am going to lower the stand such that the ball comes close to the indicator pin. So now our pendulum is ready with 150 centimeters length. Let's give a small displacement, let it oscillate and get the time for 20 oscillations. Let's get the time for 20 oscillations now. Let me reset the stopwatch to 0 again and then give a small displacement. Started oscillating. When it goes to the right side, passing the indicator, I am going to start the stopwatch. So you can see I have given a displacement. It started oscillating. So when it passes the indicator pin towards one direction, maybe towards the right direction, I will start the stopwatch. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 20 oscillations completed. The time I have got is 49.69. You can see 49.69, which I can assume as 50 seconds. 50 seconds. 49.69 is towards the 50. So 50 seconds is the time I have got for 20 oscillations. That is when the length of pendulum is 150 centimeters. What next? I have to reduce the length to another, or reduce by another 25 centimeters. That means we have to bring it down to 125 centimeters. I already have marked here. This is where the 125 centimeter mark is, right? So let me raise it up to that point. All right, so this is at 125 centimeters now. Now the pendulum ball has come up. You can see it has come up from the indicator pin by 25 centimeters. Let's bring it down. Let's bring it down. Let's bring it down the stand. Now you can see this is at 125 centimeters. Again, take the stopwatch, reset it to 0, give a displacement to the pendulum ball, observe 20 oscillations and measure the time takes for 20 oscillations. It started oscillating. I have not started the stopwatch yet. When it passes towards one direction across the indicator pin, I will start it. Let me start now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 20 oscillations. See the time I have got, 45 seconds I have got, 45. You can see it's 45. 45 seconds we have got. Yes. So see, 125 means, let's look at the equation again. T equals 2 pi square root of L over G. You know square root G is 10. So square root G means square root 10. The value of pi is also close to square root 10. So in the equation 2 pi square root of L over G, pi and square root G can be cancelled. Then what remains is 2 root L. Root L, now it is 125 centimeters. In meters, it's going to be 1.25 meters. You know, 1.1 squared has to be 1.21. So 1.25 within square root, approximately 1.1 outside. 1.1, a little bit more than that. And there's a 2 outside. In 2 pi, you cancelled only the pi, 2 remains. So 2 into 1.1, 2.2 is the answer. 2.2, a little bit more than 2.2. Right? Here we got 45 seconds, that's for 20 oscillations. So divided by 20, 45 divided by 20, approximately 1.1 is the answer you are getting.
right? 1.1 is the answer you are getting, right? 1.2, 45 divided by 20, approximately 2.2. 2.2, yeah, 45 divided by 20 is approximately 2.2. So 2 outside the square root, from the square root you get 1.1, 2.2. See, the answer verifies. So what we calculate with the theory and what we get in the experiment must be very close. There can be small errors because of the human errors, more or less it has to be same, right? So 125 centimeters we have done the experiment now, right? We got how much? 45 seconds as the oscillation time for 20 oscillations. What next? Again reduce the length by 25 centimeters, make it at 100 centimeters, and let's get the time. You can see this is where I have marked 100, this is where I have marked 100. So let me raise it up to there. And then let me lower the stand now. Let's lower it. Let's lower the stand. So now I have set it at 100 centimeters. Let me show you 100 centimeter. See. See, this is where the meter ruler 100 centimeter is, right? That is where the cork ends and the thread starts. And it goes up to see where the meter ruler starts, right at the center of the pendulum ball. That's the center of gravity of the pendulum ball. From there only we are measuring the length of pendulum. It's exactly 100 centimeters we get here, right? Exactly 100 centimeters. As we did for the previous cases, let's give a small displacement and see, observe the, measure the time for 20 oscillations. Before that, let me reset the stopwatch to 0. Give a small oscillation, small displacement, started oscillating. When it passes the indicator, I'll start the stopwatch. Now, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 20 oscillations, the time I have got is 40 seconds. See? 20 oscillations I have got 40 seconds. 40 seconds. Right? Let's double check with the equation. T equals 2 pi square root of L over G. I told you pi and root G will be cancelled. So you get 2 square root L. L is exactly 1 meter now. So square root of L, square root of 1 is 1. The 2 remains outside. 2 seconds have to be the time. And we got 40 here. That's for 20 oscillations. 40 divided by 20, 2 seconds exactly we are getting. Right. So on and off you can double check the answers like this for some known values. So 100 centimeter we got 40 seconds for 20 oscillations. We have already taken 4 readings, 175, 150, 125 and 100 centimeters. Let's take one more reading. Let's reduce the length by another 25 centimeters, make it 75 centimeter length pendulum and get the readings once again. This is where I have marked, see this is where I have marked the 75 centimeter mark. Right. Now it is at 75 centimeters. Let me bring down the stand so that the pendulum ball comes close to the indicator. Understand, if you are doing this experiment at laboratory, from where you have to observe the pendulum ball and the indicator, all that have to be in front of, like at the same eye line of yours. Eye level must be at the same level. Then only you can precisely observe when it crosses the indicator, right? Here I am standing like this and doing it because we are showing it with different equipments for you. Through a camera you are seeing it. So if you are doing it yourself, you can't stand like this and do the experiment. Make sure you sit in front of the pendulum such that the indicator is at the right eye level with you. Clear? Right. Now let me take the stopwatch, reset it to 0, give an oscillation, give a displacement, let it oscillate. I give a small displacement, started oscillating. Let me start the stopwatch. Now, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 20 oscillations, I have got the time, it's 35 seconds. 20 oscillations, I have got the time, it's 35 seconds. 35 seconds is the oscillation time we have got for 20 oscillations. So now we have 5 readings, 5 different L and the respective T values we have. We measured 20 T, divide each of those values by 20, get the T values. T squared versus L graph can be drawn. First thing we have to verify whether it is a straight line going through origin. It has to be. Second thing, the gradient of the graph should be equal to 4 pi squared over G. By taking the gradient, we know the value of 4 pi squared also, we can find G's value. Theoretically, we assume it to be 9.8, close to that, we should get from this graph also. So now, let's draw the graph and see whether we get the desired results.
I have recorded the measurements that we got on a table. L, these are the L values we have used, and time for 20 oscillations we have marked. Then I divided each of them by 20 and I got T, oscillation time for one oscillation. 20, 54 by 20 is 2.7, 50 by 20 is 2.5, 2.25 to 1.75. And I squared that as well because you remember I explained T equals 2 pi square root of L over G. So T squared is what we take in the y-axis, 4 pi squared over G into L. This is what we take in the y-axis, y equals mx. Yeah. So T squared, each of those values I have squared and I have got these values. Now we need to draw the graph. Draw the graph. Let's draw the axis. This is going to be T squared second squared. This is L in centimeters. L you need up to 175. 175. So that's like, let's say, we'll put 25 here. 4, 6, 8, 10, 12, 14, 16, 18, 20, 24, 22, 24, 26, 28. So we'll take it like this. 25, 50, 75, 100, 125, 150, 2, 4. This point will be 175, right? And the y readings, y has to be t squared, which goes up to 7.29, 7.29, 1, 2, 3, 4, 5, 6, 7, 8. First point is that 175 and 7.29. 175 and 7.29, 7.29, 7.5 is here, 175 is here, 7.29 should be here, correct? Yes. 150, 6.29, 150, 6.29, 6.29, 6.29, 6.29, that will be 6.29. 125, 5.06, 5.06, 5.06, 5.06, 125, 5.06. Almost 5, right? 5.06 is almost 5, almost 5. Next, 104, 104, 4, 4, 4, 4, 4, 100, 100, 100. 50 and 3.06, 50 and 3.06, 50 and 3.06. 100 we got 4, the last one. Oh, this was 75, not 50, 75, right? 75, 3.06, 75, 3.06, 75, 3.06, here. That's it. Those are the values we have got. We are expecting a line through origin. Let's see if we get that. Right, that's how the graph is going to be. Am I right? Check that. Yes, that's how we get it. Starting from origin, can you see these 3 points lie on the graph? Those two have a slight deviation, that's okay. Slight deviation is okay. Now what we need is the gradient. Gradient is going to be, we'll take 2 points, maybe this point is good, or even this point. This is 25 and 1, 25 and 1. We'll take another one, maybe according to the graph, the point we get is 150 and 6, 150 and 6. The original point for 150 is a little bit deviated from the graph. So after drawing the graph, don't take the previous readings. Now on the graph, you take 2 points. On the graph, you take 2 points. Let's take the gradient. Gradient has to be 4 pi square over g, which is equal to 6 minus 1 over 150 minus 25. Pi square, let it be 10, g, 5 over 125. 5 over 125. Wait. This is in centimeters, multiply by 10 to the power minus 2 into 10 to the power minus 2. 10 to the power minus 2 means I can take it up and put it as 500. Yes. So if you cancel this is going to be 4. 4 and 4 cancel, you get g equals 10. 9.8 is the correct value, but based on the experimental values that we have got, we get 10. 9.8 is the actual value, but we get 10. That's fine. That's fine based on the graph that we have done, because any experiment, there will be experimental errors. Like when you measure the time, there could be error. Measuring the length, there could be error. Because of the air drag, the time is going to reduce little by little. First oscillation and 20th oscillation will not actually have the same timing because of air drag. So all these errors would have a small impact on your final answer. However, 10 is a very close answer for the gravitational acceleration. Clear? So, that is a very simple experiment. I have shown you the experiment and I have done the calculations. Now, let us see how this has been tested in the past papers. Students, let us see the past paper questions on this experiment. This is from 2006 paper. A student plans to find the acceleration due to gravity in the laboratory using a simple pendulum. They have given an image here. Pendulum's length is L, right? It rotates through angle theta towards that side. They mark 2 points as A and B. Let us see what it is about. Write down an expression for the period of oscillations t of the simple pendulum in terms of the length L of the pendulum and the acceleration due to gravity. We all know that is a giveaway question, so simple, 2 pi square root of L over G. 1 mark, so easy, got it. Rearrange the above expression in the most suitable manner in order to obtain a value of for G by plotting the graph. Again, another simple one, T squared is going to be 4 pi squared over G into L. This is going to be Y, this is going to be X, this will be M. When taking readings for T, the student keeps reference pin directed at the point B as shown in the above diagram. State why directing of this pin at B gives a better accuracy for the time measurement than directing at point A. So, whether you are going to keep the pin here or here is the discussion. He said student has decided to keep it at B. B is the lowest point, see. So, why do we keep it at the lowest point, not anywhere else? This is where the speed will be high. So, see, like the pin is going to be like this. When the thread passes it very fast, then the error will be less there, right? Imagine if the pin moves very slowly, to pass the pin itself it is going to take some seconds, right? Say half of the second it takes. Then at which point you assume as it passes the point? Imagine if the pin is, if the thread is too small, too slow, if the pendulum is too slow, to pass the pin it takes some time. So, whether at the beginning of passing it or at the end of passing it, when are you going to take it as passing the point can be a confusion. But when the pin is here, if the pendulum passes it very fast, the time it takes just to pass this pin is minimized. Time that takes to pass the pin is minimized. That is why we always prefer keeping it at the lowest point, because the speed is high, pendulum speed will be high. Yes. So, we can say at B the speed will be highest. The time to cross the pin or pass the pin is minimized, is lowest. It's the lowest, This is the lowest. When the student measured the time for only one oscillation, his reading was 2 seconds. If the instrumental error in time is 0.1 second, determine the percentage error value of the period of oscillations. 2.1 into 100. They said percentage oscillation, right? So, it is going to be 10 by 2, 5%. 5%. Instead of measuring the time for one oscillation, he measured the time for 25 oscillations and the value obtained was 50.2 seconds. Determine the percentage error of the value of the time measurement. See, basic stuff they are asking, basic stuff. So, it is going to be 10 divided by 50.2. 1, then you get 498. So, this is going to be 9.19. Yeah. So, they say to the nearest first decimal place, we can give it as 0.2, 0.2%. The student used a uniform metal sphere of radius r as a pendulum bob. The length L he used as the length of the pendulum is shown in the diagram. After plotting the t squared versus L graph, he found that the gradient was 4 and the intercept was 0.04. Rewrite the expression in part A in terms of L and R. Now look at this. Look at this. The pendulum's length is going to be this much. So what we used as L is actually capital L plus R. So T squared equals 4 pi squared over G into L. Instead of L, now I am going to write L plus R, because capital L is the length of the string only and R is the radius of the sphere. Remember, I told you the length of pendulum has to be measured from the center of the sphere. So L plus R has to be the length of pendulum. Right. Rewrite the expression in part A in terms of L and R. Determine G. So now look at this. T squared 4 pi squared over G into L plus 4 pi squared R over G. This is 1, this is Y, this is X, M and C. So anyway, the gradient is 4 pi squared over G. They have given the value of gradient. Gradient is 4. Gradient is 4. Gradient 4 pi squared over G is 4. So G is pi squared, which is approximately 10. Which is approximately, they said take pi as 3.1. Wait. 3.1 squared. 31, 93, 961. 9.61 ms minus 2. 9.61 ms minus 2 is what you get. Careful, they said take pi as 3.1. Next, determine the radius R of the sphere. R is going to be, look at this. See, here you have 4 pi squared over G, here you have 4 pi squared G into R, right? So take the intercept, divided by gradient, you will have only R. Intercept by gradient. R is going to be intercept by gradient. Intercept they have given 0.04, isn't it? Intercept they have given 0.04. Where? 0.04. Gradient is 4. You get 0.01 meter, which is 1 centimeter. 1 centimeter. 1 centimeter. The student observed that the amplitude of the oscillations gradually decreases with time and the bob finally comes to rest due to air drag. He repeated the above experiment with a wooden sphere of the same radius. Which bob would take less time to come to rest? Give reasons for your answer. Which will take less time, that means which will damp faster, which will come to rest faster? The wooden bob or wooden sphere. The reason is, since it has less weight, since it is less dense, less weight, the impact of air drag will be significant, will be more, right? Since it is of density and weight, the impact of air drag on wooden sphere is more than that on which one, the other one? Wooden sphere of the same radius. The student observed the amplitude of oscillations gradually decreases with time and the bob finally comes to rest due to the drag. He repeated the above experiment with a wooden radius. So what was the previous one he used? Uniform metal sphere. Clear? Simple to understand. See, from top if you put a metallic ball and a woolen ball, the metallic ball falls faster. same sized woolen ball, because of the air drag, sometimes it might not even fall directly, it might, go here and there and fall. It takes more time, which means the impact of air drag depends on the weight, not only the size. Even though the size is same, the metallic ball will fall faster than the woolen ball. So, similar concept is there for pendulum also. Metallic ball and the wooden ball is less weighted, therefore, it will have more impact due to the air drag. Clear? Right, this is another question. This is from 2015 paper. Figure 1 shows the motion of a simple pendulum of length L. Write down an expression for the period of oscillation T of the simple pendulum in terms of L and acceleration due to gravity G. That is simple. T equals 2 pi square root of L over G. Alright. If the laboratory experiment to find the value of G using the simple pendulum, you are provided with a stopwatch which can measure the time with an accuracy of 0.5 seconds. If the estimated value of the period T is 2 seconds, determine the maximum number of oscillations you should take to reduce the percentage error of T down to 1%. Alright, let us see. If you want to reduce it to 1%, 0.5, 2 into n number of oscillations, it must be 1%. Yep. So, percentage multiplied by 100. See, this is the error, this is the measurement we take, 2 seconds into number of oscillations into 100. This has to be 1%. So, this is 50 by 2, n is 25. So, if you take for 25 oscillations, then you can have the percentage error to be 1%. A student has designed an electrical method to determine the period of oscillation T more accurately by using a detector system. So, this is where he has a source diode and this is where he has the detector diode. And from here it goes to a computer. Now, this is how the gadget looks like it looks like a small magnetic thing. When the pendulum passes through the middle, like from the source diode, there is a ray, IR beam, infrared beam goes to the detector. When the pendulum crosses this beam, the signal is going to be disconnected, right? The receiver, detector will not receive that signal, right? So, let us see what he does. The detector system consists of a source diode and a detector diode. Source diode emits a narrow beam of infrared light with a constant intensity of L naught. This light beam is detected by the detector diode and it also measures the intensity of the beam. Detector system is placed in the path of the bob of the simple pendulum. While oscillating, the bob also crosses the IR beam. Whenever the bob interrupts the IR beam, the detector diode signal becomes 0. Otherwise, it produces a signal of constant L naught. When the bob is oscillating, the computer monitor displays a graph of the value variation of the detector signal intensity L and I. So, simply what happens, always see, like if there is no pendulum, the detector will continuously receive the infrared beam, the signal will be continuously there. But now what is going to happen when the pendulum crosses it time to time, you will have like this, signal comes, then when the pendulum crosses it, you do not have signal, again crosses it, again signal, crosses it, likewise it goes, right? Understand? It's very simple. If the pendulum does not cross, then it will always be the signal like this. When pendulum crosses it, for the pendulum bob to pass that IR ray, it takes a while, right? Within that time gap, there is no signal, it is 0. Figure 3 shows such a graph, here you go, displayed on the computer screen, and it is taken in a situation where the force due to air drag is negligible. Air drag is negligible. The time interval corresponding to the 0 detector signal is T0. This gap is T0, T0, T0. Value of T naught depends on the speed V with the bob crosses the, when the when the bob crosses the IR beam and the diameter d of the bob. Yes, because see, this is how the bob is going to be, right. So, if the IR beam is at this point, the time it is going to take d divided by v. D is this distance. So, entire distance has to finish passing the IR ray. Velocity is v. D divided by v will give you the time. What will happen to the value of t naught when v is increased? When v is increased, it will pass quickly, right. So, t naught will reduce. T naught reduces. Related to d, when d is increased, t naught also will increase. Because you are using a bigger bob, it will take more time to pass that beam. T naught increases. T naught increases. Write down an expression to estimate v in terms of d and t naught. Yes. So, v is going to be the distance divided by time, d over t naught. What is the value of t according to the graph given below in figure 3? T means the oscillation time. Look at this. Now see the beam, let us say the beam is going perpendicular to this plane. Okay. The pendulum goes here, comes back and comes back. This is what you call one full oscillation is. So, when it goes rightwards, it first let us say this is where number 1, number 2, number 3 again is going to cross it. So, this is where number 3 is 1, 2, 3, 4, 5. That is how one full oscillation is going to be. 5 will be at this point. Or if I name it as A, B, C, D, E, look at this again. Numbers can be sometimes confusing. Okay. Let us say when it starts, this point is A, that is here A, B, C. When it returns, this point is C, that is going to be here C, because when it returns also it crosses the IR beam. D, and again it returns to the initial position E. E is here. So, one full oscillation means from here A to E is what you call one full oscillation. It takes 3 seconds. Can you see? 3 seconds from 0 to 3 seconds. So, T is 3 seconds. Student, place the detector system at the most appropriate position of the path of the bob to determine the maximum speed Vm of the bob, and obtained a graph similar to the graph shown in figure 3. With respect to figure 1 above, given the position A or B at which the student should keep the detector system in order to determine V maximum. V maximum is at the lowest point only. The velocity will be maximum for a pendulum at the lowest point. Give the reason for your choice. Let us see where they have marked AB. Where is the pendulum? AB. A is the lowest point. That is where the Vm velocity is maximum. So, he has to place the detector system at point A. So, A, the speed of the bob, is maximum at its lowest point. Because what happens when it goes up and up, the potential energy increases. So, the kinetic energy reduces. So, when it goes up and up, the velocity reduces. When it comes down, potential energy reduces because height reduces. So, kinetic energy increases. How can the kinetic energy increase? Velocity can increase. In order to carry out this experiment, the student says that the cylindrical bob shown in figure 4a is better than the spherical bob shown in figure 4b. If both bobs have same diameter d, give a reason to justify his statement. Imagine now the beam goes like this. Now, if your beam is like this is how we have to exactly set it up if you are using a spherical beam. But the problem is, in daylight, the infrared ray will not be visible to us. We will not be able to see the infrared ray. then how do we know whether it passes through the diameter itself? What happens if it is like this? Still in the monitor, when you observe the signal, you will see the monitor gets stopped, because when this part passes the infrared ray, anyway the signal gets disconnected. But you wouldn't know whether it is through the diameter or not. Actually, if this is the case, if this is how the arrangement is made, it is not passing through the diameter. This gap is going to be something else. This is not D. Understand? So, since infrared rays may not be visible to eyes, you won't be able to ensure that the ray goes through the diameter of the spherical bulb. But if it is a cylindrical bulb, wherever it passes doesn't matter, right? See, if the beam is like this, still it has to cut the distance of D. Here D, here D. So, wherever it cuts, it has to anyway cut the distance D. That's why he said this is better than that. So, he is asking now, what is the question on us? If both bulbs have the same diameter D, give a reason to justify his statement. Okay. So, let us say the IR ray may not be visible when we use spherical bulb. It is difficult to ensure that the ray passes through the diameter of the bulb. If bulb is used, this issue doesn't arise. This issue doesn't arise. The student decided to calculate Vm using the graph mentioned above and the expression in C2. Can he get exact value for Vm by this method? Explain your answer. Graph method and the expression C2. Now, the problem is, now see, since there is going to be R track and all, if you take the point here, it's just an instantaneous speed. We can't say that is going to be the V maximum always. After a couple of oscillations, it can be a different value, right? So, when you count 25 oscillations, each oscillation, the velocity maximum velocity could be different. So, what you would measure from this might be an instantaneous value, not the average value, right? So, let us mention that. Know what is measured from the graph is an instantaneous value. Instantaneous value is an instantaneous value. The student observed that in a situation where the force due to air drag is significant, the maximum speed Vm that be obtained decreases considerably from oscillation to oscillation and the bob finally comes to rest. For such a situation, complete the graph I with t that you would expect for a period time t on the figure, right. So, what he says is air drag is significant. So, first time it passes faster, second time it is going to be slower than the first time, third time it is going to be even slower. So, what will happen, that time t naught will increase because it passes slowly. So, now look at the graph how it is going to be. Let us put the vertical lines first. Okay, let us say T0, yes, correct? That's how the graph is going to be. What do we note here? See, the time gap here and time gap here, can you see? This must be bigger. It takes more time than the previous time because it started going slowly. If the maximum speed of the bob at t equals 0 and t equals t are 0.44 meter per second squared per second and 0.42 meter per second respectively, estimate the energy loss of the pendulum due to air drag during time t 0 to tt. Energy loss, kinetic energy loss, right? Half m is 100 grams, 100 by 1000 to change into kilograms. V1 squared is 0.44 because what I am doing is half m V1 squared minus half m V2 squared. Take half m common, you will have V1 squared minus V2 squared. V1 squared minus V2 squared. That's what I am doing here. So that's going to be half. This is 0.1. This one, rather than squaring it, we have a shortcut for it. A squared minus b squared can be factored. Difference of squares can be factored. How? A minus b, a plus b. We have a factoring method like that. Use that idea here. Subtract it, you get 0.02. Add it, you get 0.86. See how easy that is. So it's going to be 0.01. So 1, 2, 3 decimals here. 8.6 into 10 to the power minus 4 joules. 8.6 into 10 to the power minus 4 joules. That much of energy loss is there compared to the first case to the second case. Clear? So that question is out of the usual pendulum experiment, but they can nicely connect other parts of mechanics as well into any experiment that we do. Right? So that's all about that experiment and the past paper questions. I hope you would have understood and all this would have been useful to you. Practice this again and again, then only you can face what you get in the exam comfortably. Next time, let's meet up with another experiment.